Okay, so let us talk about the interfacial boundary condition, that is the boundary condition at the interface between two fluids. Okay, so we will talk about the kinematic boundary condition as well as the dynamic boundary condition. The kinematic boundary condition would require that the normal component of the velocities across the interface are the same, and the tangential the the dynamic boundary condition would require that the tangential component of the velocities across the interface they are the same. Also it would require the balance of the stresses at the interface, okay, the balance of the fluid stresses with the surface tension stresses, okay. Interfacial boundary conditions. So let us draw a surface interface. So let us say this is an interface between two fluids, okay. So this is the interface, and let us say this is fluid 1 and this is fluid 2. So let us say this is UN1 and which is equal to U1 dot unit vector along the normal. This is UN2 which is U2 dot n cap, okay. So this is the vector sign, okay. So the kinematic boundary condition would require that the normal velocity is continuous across the interface, so we would have UN1 will be equal to UN2, okay. So UN1 will be equal to UN2. Then we talk about dynamic boundary condition, which is important when the two fluids are moving, okay. So it is a moving interface. So in that case we will say that the tangential component of the velocities ut1 will be equal to ut2, right. So the tangential velocity is continuous across the interface, okay. Let us talk about dynamic boundary condition for stresses, okay. So the dynamic boundary condition for stresses. So we know the fluid stress is given by this expression. So tau dot n cap, this is actually a tensor, so we have double arrow, minus p n dot plus eta del u over del eta plus eta del un, okay. So that is the expression for the stress tensor. Now the interfacial stress interfacial stress due to surface tension So, the interfacial stress due to surface tension will have two different components. One will be in the tangential direction, okay, which will be due to the spatial variation in the surface tension, okay, if there is variation in the surface tension along the interface, and the other component is in the normal direction, which is because of the radius of the curvature of the interface, okay. So, the interfacial stress due to surface tension will have two components. One is the spatial gradient of surface tension, right, and the other one would be due to the interface curvature. So, these two will contribute towards the interfacial stress due to surface tension. So, we can write the dynamic boundary condition to be tau 2. So, this is on the fluid 2 side minus tau 1 dot n, okay, will be equal to gamma del dot n into n cap minus gradient of surface tension minus n cap dot gradient of surface tension. So, that is the boundary condition at the interface, where we have tau 1 and tau 2, tau 1 and tau 2 are the fluid stresses in domain 1 and 2. So, this is due to pressure and viscosity, okay, and the normal stress due to surface tension is this component here. So, this is del dot n, so which is equivalent to 1 over R1 plus 1 over R2, okay, for a simple case, and the tangential stress is the gradient of the surface tension minus n cap dot gamma. This is the tangential component of the surface tension stress. This is the normal component of the surface tension stress. So, the stress due to the surface tension is balanced by the fluidic stress, that is what we see here. Now, if we split this into two different components, this stress balance into two different components. So, we can write in the normal component we can write tau 2 dot n cap minus tau 1 dot n cap dot n. So, that is making it in the normal component, right, will be equal to gamma del dot n. So, this can be simplified and written as, so this can be written as P1 minus P2 plus 2 eta 2 into del u n 2 divided by del eta minus 2 eta 1 into del u n 1 over del eta will be equal to gamma into 1 over R1 plus 1 over R2. So, this is the normal component of the stress balance at the interface. Now, for a static interface, if the fluid is not moving, then the velocity will be 0. So, stationary interface stationary interface u will be equal to 0. So, we will have P1 minus P2 as gamma into 1 over R1 plus 1 over R2, which is nothing but the Young Laplace pressure drop. Okay. And you can write the tangential component also, tangential component. So, we can write tau 1 dot n minus tau 2 dot n, so dot t will be equal to, so that makes it tangential component gradient of the surface tension minus n cap n dot gradient of surface tension into t dot. Okay. So, if we simplify this, we can write eta 1 del u t 1 over del eta plus eta 1 del u n 1 over del t minus eta 2 del u t 2 del eta minus eta 2 del u n 2 over del t is going to be minus gradient of surface tension minus n cap into n dot. Okay. So, this is the tangential component of the stress balance at the interface. Okay. So, next we move on and talk about Marangoni force. Marangoni force comes into play when we have gradient of surface tension. Okay. So, we can say Marangoni force and this is because of the gradient of surface tension. We can define Marangoni force. So, F Marangoni is gradient of surface tension. Okay. So, let us say we heat water, okay, from let us say 50 degree to 70 degree, the surface tension will change, okay, at different locations depending on how we are heating. Okay. So, because of the heating, the surface tension can change and which can induce the force for the fluid to move in certain direction, okay, and this is possible because of the Marangoni force. Okay. So, this gradient of surface tension is possible because of heating. It is also possible by addition of surfactant. Okay. So, let us say one example we consider is if we heat water let us say between 20 degrees to 25 degrees C, the surface tension gamma will change from 72.9 at 20 degrees C to about 72.1 at 25 degrees C. Okay. So, it is millijoule per meter square. So, you can achieve a gradient in the surface tension if you can manage the way you are heating water. Okay. The second example we would consider is how bacteria propel themselves. Okay. So, bacteria cannot move of their own by applying some force themselves because they are very tiny. So, what they do is they eject some fluid at their back. So, that ejection of the fluid which acts as a surfactant causes a gradient in the surface tension. Okay. And since the gradient of the surface tension is positive in the forward direction, they propel themselves, okay, in the forward direction. Okay, that is how bacteria move. So, another important consequence of the Marangoni force is bacteria use gradient of surface tension or movement. The other example we can consider is if you have a stick and you can attach a bulb of soap at the end of the stick and you put it on a water surface, then because of the soap dissolving in water and reducing the surface tension locally, you can induce a gradient of the surface tension which would cause the stick to move in the forward direction. So, as another example you can use build a small boat by attaching a piece of soap at the end of a stick. Okay, it is possible to do that, right. So, with that we finish the chapter on capillary flows and surface tension. We move on to the next chapter which is on electrokinetics. Okay. So, for many microfluidics applications we would require to move bulk of the fluid inside a channel, or we need to move particles inside the microchannel. The particles may be either charged or uncharged. Okay. So, it is important to study electrokinetics. So, electrokinetics can be studied if we talk about electrohydrodynamics, where we talk about the coupling between electrodynamics and hydrodynamics. Okay. So, in the electrodynamics we will briefly talk about electrostatics. Okay. So, this is what we will be concerned about in this particular course about electrostatic, and we will not consider the magnetic effects when you talk about electrokinetics. This is because we will be dealing with charges which move relatively small, very small as compared to the movement of electrons inside wire. So, the magnetic field that will be created in case of microfluidic channel flows where charges will be flowing through will be very small, it will be negligible. So, our assumption that magnetic effects are not important is valid in this case. Okay. So, let us very briefly talk about electrostatic. Okay. So, we talk about electrokinetics. And this is important because in many lab on chip applications we need motion of liquid or particles. Okay. So, to study electrohydrodynamics is important, and here we will be studying the electrostatic regime, and the magnetic effects negligible. Okay. So, briefly we will talk about electrostatic. So, let us say if we consider a point charge q in a space, one important consequence of it will be the influence it will have on the surrounding, okay, and which can be represented in terms of the electric displacement. Okay. So, the electric displacement which is given by the symbol d will be q divided by 4 pi into unit vector r cap divided by delta r square. Okay. So, what electric displacement represents is, if you have a point charge in a space, what its effect is going to be on the surrounding, okay, and its effect in terms of electric displacement is going to look like q over 4 pi into r cap over delta r square, where delta r is the distance between the origin of the charge to a particular point where we want to see its effect. Okay. And this electric displacement is going to be radially outward. Okay. So, this electric displacement, this is the charge and this is the distance in radial direction. Okay. So, now this electric displacement has got two components. Okay. One is the electric field it will induce, okay, and the second one is the polarization. Okay. So, we can write electric displacement d in terms of epsilon 0 into electric field plus the polarization. Okay. And we can write this as epsilon 0 into E into 1 plus a term called psi. Okay. So, this psi, so here we have different terms, this is the electric field, right, we will define it here, is the electric field, and P is the polarization, and epsilon 0 is permittivity of free space, and psi is the susceptibility, electrical susceptibility. We have equivalent magnetic susceptibility also. So, if you look at here, as I said, electric displacement has two components, one is the electric field that the point charge will create and the other one is the polarization. Now, if you consider this, we can also write it as epsilon into E, okay, where 1 plus psi is known as the relative permittivity, okay, epsilon r is relative permittivity. Okay. So, epsilon 0 into 1 plus psi is or epsilon 0 into relative permittivity is the permittivity of the medium that we are talking about, permittivity of medium. Okay. So, this is an important equation in electrostatic. Now, if you talk about free space, okay, talk about vacuum, we do not have anything present, okay. So if you put a point charge in vacuum there will be nothing to polarize, okay. So all its effect will be to create, to induce an electric field, okay. So here you can see that for vacuum, for free space, the polarization is going to be 0, right. And so as a result you can see here the psi, okay, will be 0 for free space, right. Now if you talk about a charge in water, okay, because water molecules are present, the charge would have effect in terms of inducing an electric field as well as polarizing the medium, okay. So if you use let us say water, so water as the medium, then the charge would induce electric field plus it will also polarize, okay. Now if you consider the permittivity of water is about 80 times that of the free space, okay. Now how do we compare, if the permittivity is 80 times that of free space, if you put a charge in water, whether it is going to create more field or it is going to polarize more, okay. And this can be answered if you look at this equation here. If you look at this equation here, okay, then we can see very clearly that since this is going to be 80 times epsilon 0, okay, so this is 80, this is 1, so psi will be about 79. So about 79 part of the influence of the charge would be to polarize the medium and only one part of it would create an induced electric field, okay. So what this means is that the water medium gets more polarized than the induced electric field, okay. So apart from these two equations we have few more important equations to write. So the one equation is the electric field is irrotational, so del cross E will be 0, okay. So from which we can also say that the electric field will be negative of the gradient of the potential, phi is the potential, electric potential, okay. Then we can also write the Gauss law, which tells that the divergence of the electric displacement will be the divergence of epsilon into E, that is something we know, and so that will be equal to the electric charge density. This is also an important equation, okay. So divergence of the electric displacement is the electric charge density. Now from here E equal to minus del phi, if you substitute in this equation here, what you would get is del square phi r will be equal to minus 1 over epsilon into the charge density, okay. So this is more easy to solve as compared to this, considering a physical situation, because in physical situation we have the voltage boundary conditions, that is specified for a given case, whereas charge density is it is very difficult to specify, okay. So this equation is very important. From here we can write the expression for the force for the electrical force is the charge density into electric field, okay. So this is the expression for the electric field in terms of the charge density and the electric field, okay. So if you know the charge density present in an electric field, we know how much is the electrical force that is acting. Now the effect in electrohydrodynamics, we have to consider the coupled electric field as well as the hydrodynamics. The effect of the electric field is taken into account by considering this electrical force as a body force in the Navier-Stokes equation. Similar to in case of buoyancy, we have the GH term, the gravitational term will be important. In this case the electrical body force term will be important. So so the coupling, the electric field and hydrodynamics coupling is achieved by using electrical body force in the Navier-Stokes equation. So we can write this way, we can write rho del V, I am using T notation here as the gradient of del V over del T, plus V dot del into V, this is the convection term, will be equal to minus del P plus eta del square V plus rho into G plus rho electric, the charge density into electric field. So that is the Navier-Stokes equation for electrohydrodynamics, okay. And this is the electrical body force term, electric body force, okay. So with that introduction, let us move on and talk about three different important electrokinetic effects. One is electroosmosis, second one is electrophoresis, and the third one is dielectrophoresis. So before we go on and talk about these three effects in detail, we will very briefly see what these three effects mean, okay. So the first one to talk about is electroosmosis. Electroosmosis is the bulk movement of a liquid relative to a charged surface by application of electric field, okay. So we have three different electrokinetic effects: electrokinetic effects, okay. So the first one is electroosmosis, second one is electrophoresis, and the third one is dielectrophoresis. Okay. So let us look at the first one, which is electroosmosis. And this is nothing but bulk movement of an ionic liquid relative to a charged surface surface due to an electric field. Okay. So, in this case let us consider we have a glass capillary. Okay. So, this is made out of glass and we have an ionic liquid present, ionic liquid, that means it has non-zero electrical conductivity. Okay. And if we apply a potential difference across the glass capillary or glass channel, then we will induce a flow in this direction. Okay. So, this is the electroosmotic flow. Okay. So, this is because if you look at the surface of the glass, it will have this silent bond, SiOH bonds. Okay. And if you have a pH 7 liquid here, let us say this is pH 7 liquid, what happens is these protons they get knocked off. Okay. So, these protons fall off, and when they fall off, the surface gets a net negative charge. Okay. So, if you look at the microscopic layer close to this wall, what happens is this. What we see here is the wall is negatively charged. Okay. So, this is negatively charged and these charges do not move. Okay. So, these are almost fixed to the wall, and so we have positive charges which get attracted and come towards the wall, positive charges from the liquid, from the ionic liquid. So, if you look at in a layer close to the wall, we would have more positive charges as compared to the negative charges. Okay. More positive charges as compared to the negative charges, and the bulk will be uniform. So, you will have equal number of positive and negative charges in the bulk. So, this will be bulk will be neutral, and across this layer which is called the electrical double layer, as we would be discussing later, the electrical double layer in this case will have a net positive charge. Okay. Because the wall is already negative, so we will have more positive charges in the fluid in the electrical double layer. Now, if you apply a potential difference here, these positive charges will tend to migrate towards the negative electrode. So, we will have a bulk motion of the liquid in this direction. Okay. So, this is the electroosmosis phenomena. The second electrokinetic phenomena that we will talk about is called electrophoresis. In electroosmosis, we are talking about an ionic liquid in a capillary or in a channel. So, we are not talking about any charges here. However, in electrophoresis, we will have charges present inside the channel in some liquid, and if you apply a potential difference between the ends of the capillary or the channel, depending on whether the charge is positive or negative, they will migrate towards opposite electrodes. Okay. And this effect is known as electrophoresis. Okay. So, we talk about electrophoresis. Here we have a capillary or a channel which has some charged particles, so negative charge, positive charge, and we have electrodes. Let us say this is anode and this is cathode. So, when we apply this electric field, the charges will migrate towards opposite electrode. okay. So and because of that these charges would get separated. So the definition of electrophoresis would be movement of charged surfaces. So these charged surfaces they may be dissolved in the liquid or they may be undissolved. So for example in case of DNA in some buffer because DNA has got a negative charge because of the phosphate in the backbone. So you know it is not dissolved in the buffer, it can be separated, different DNAs depending on their mass to charge ratios they can be separated, whereas things like you know the dissolved charges in sodium chloride for example, okay. So these charged surfaces can be either dissolved or undissolved. So movement of charged surfaces relative to a stationary liquid due to applied electric field. Okay. So one example is separation of DNA. So what we will see later is you know in addition to movement of these charges the bulk of the liquid is also moving, okay, because electroosmosis is a much stronger effect as compared to electrophoresis. So always there will be movement of the liquid itself going towards a specific electrode, but because of the charges you know in the charged particles they will tend to migrate towards opposite electrodes. So there will be a net effect if something you know if the fluid is if the capillary is made out of glass, the zeta potential is negative, the electroosmosis will happen from positive to negative electrode, and if you are talking about you know two different charges positive negative, the positive will go towards the negative electrode, the negative will tend to go towards the positive electrode, so they will get separated, okay. So and so the application of electroosmosis we can write is electroosmotic flow, electroosmotic flow in microchannels. Now let us talk about what is dielectrophoresis. So we talk about dielectrophoresis. So dielectrophoresis is the force exerted on dielectric or neutral particles subjected to non-uniform electric field, subjected to non-uniform electric field, okay. So one application of dielectrophoresis would be to separate neutral objects like cells, okay, based on their physical properties. Dielectrophoresis as I said is the bulk is the movement of these neutral objects or dielectric objects when they are subjected to a non-uniform electric field, okay. So if you look at this image here we talk about an object, okay, shown in the blue color and present in a medium, okay, and we have a voltage difference applied between a spherical electrode here and a flat electrode there, and because these two electrode shapes are different we have a non-uniform electric field present here. So the electric field is more positive in this direction, so the gradient of electric field is positive in this direction. So here this is the first case, okay, this is case 1, this is case 2. In the first case we see that the permittivity of the the object is more as compared to the permittivity of the medium, okay. So this is the relative permittivity of medium, and this is for the object, okay. So since the relative permittivity of the object is more as compared to the medium, you can see that the object is more polarized as compared to the medium. You have more charges present here as compared to in the outside medium, okay. So as a result we have a net polarization which is happening in this direction, okay. So here the polarization is in this direction, but the gradient of the electric field is positive in this direction. So in this direction the gradient of the electric field is positive, okay. Now as per definition of the dielectric force, which we will be discussing later, the FdP is the polarization dot gradient of the electric field. So since here the polarization and the gradient of electric field are opposing each other, okay. So let us consider this as the positive direction, okay, x positive. So this is the polarization is in the positive direction, but the gradient of the electric field is in the negative direction. So the dielectric force will be in the negative x direction. So the dielectric force is going to be in this direction, okay. So what it means is that the object is going to go towards the higher electric field or the positive electric field gradient, okay. So this is known as positive DEP, positive dielectrophoresis, where the object or particle moves towards higher electric field, okay. And if you look at the situation on the right, the second case, here we say that the medium is more polarizable than the particle. So you have more charges on the outside in the medium as compared to that inside the object, okay. So we have a net polarization which is in this direction, okay, and the gradient of the electric field is also in this direction, is positive. So we would have the dielectric force in the positive direction, okay. So in this direction, so you can say that according to this the dielectric force will be in this direction. So here this is known as negative dP, and here in negative dP we mean that the object or particle moves towards lower electric field, okay. So that is what is happening, the lower electric field is in this direction and the object gets a dielectrophoretic force which takes it towards the lower electric field, okay. So we know the application of electric field, it can be applied to certain neutral objects like cells, okay, depending on its physical properties, okay. And if we talk about positive dP, the particles or the objects will be moving towards the positive electric field, gradient of the electric field, and if you talk about negative dP, the particles or cells will move towards the lower electric field, okay. So the application of dP application is into sorting of cells based on physical properties. Okay. So, with that let us stop here.